This problem discusses an LC circuit, which consists of basically capacitor and an inductor connected in series. There is no battery in this circuit, so power is in principle lost in both the inductor and the capacitor. But we will see that this oscillates between the two. The interesting part is that inside the inductor, the energy is stored in the form of magnetic field inside this inductor, and in between the plates the energy is stored uh, in the form of electric field. So it's electric field. So energy is stored as electric field inside a capacitor, and energy is stored as magnetic field inside an inductor, and this energy oscillates between these two components. Kirchhoff's law tells us that the potential difference across the inductor, that's L I by dt, and the potential difference across the capacitor is overall equal and opposite. So together they are equal to zero. We use the fact that I is dq by dt, so rate of change of charge. And if we divide out by L, what we learn is that the second derivative of q with respect to time is equal to minus 1 over LC times q. It's convenient to define the angular frequency as, or angular frequency square, as 1 over the inductance times the capacitance, and this differential equation then takes the form minus omega square times q. This is equivalent to asking what is the mathematical function whose second derivative gives the function itself. There are exponential, there is sine, there is cosine. So the two of the independent of these are the sine and cosines, or one can write it as exponential of positive and negative argument. So the general solution for this differential equation is some arbitrary constant a. This is a second order differential equation, so it will be written in terms of two constants. So it's a times cosine omega t plus, let me not use b because usually we use magnetic field in this uh, context. So c is the capacitance, so d probably is a suitable letter. So a and d are constants of integral. Derivative of charge is the current, so current as a function of time is derivative of this charge, so it's minus omega a sine omega t. Right? Cosine function when differentiated gives sine, and the argument as omega in front of t, so it turns out the negative sign is because cosine differentiation of cosine function is minus sine function. That's plus omega d cosine omega t. We use the boundary conditions that charge at time t is equal to 0 is q naught. So q times t equal to 0, that's q naught. And on the right hand side, we have a plus 0. Cosine function is 1 at time t equal to 0. Sine function is 0. So this immediately implies that the constant of integral a is q naught. Similarly, current I at time t0 is equal to 0. That's our second initial condition. And that's equal to minus omega. So that's 0 actually. Sine function is 0 plus omega times d, because cosine function is 0. This implies that d is equal to 0. So overall, a equal to q naught and d equal to 0. So that gives us the charge as a function of time is simply Q naught times cosine omega t. D is equal to 0. And the current function of time is minus omega times Q naught times sine omega t. That's the solution that we have for the charge and the current. And of course, the angular frequency is given in terms of the inductor, inverse of the inductance and the capacitance. This is used in radio receivers to tune to a channel. So whenever LC is equal to the frequency that resonates, and let's calculate what the capacitance should be in such a circuit. So we start from omega squared, which is 2 pi f squared is equal to 1 over LC, so it's part B. So C would be equal to 1 over 4 pi square frequency square times inductance L. So it's 1 over 4 pi square. Frequency is 5 megahertz, so it's 5.0 into 10 raised to 6. And we have to square this times inductance, which is 1 millihenry, so it's 10 raised to minus 3 units of Henry. So that's the same as you have 5 square, that is 25. 25 and 4 is 100. So that's the same as 1 over pi square times 10 raised to 12 plus 100, that's 10 raised to 14, and minus 10 raised to minus 11. So in the numerator, this becomes 10 raised to 12, 14, 14 minus 3 is 11. So it's 10 raised to minus 11 farads. 1 over pi squared. So that's 0.10 into 10 raised to minus 11 farads. That's 1.0 into 10 raised to minus 12 farad, which is 1 picofarad. That's a amount of capacitance that will lead to a resonance, or which means that it will tune the radio receiver for that particular capacitance. Let me stop the sharing and stop the recording.